Okay, so let's get started. So we're going to talk about Host's proof of a Sumset conjecture of Erdős. This one was first proved by Joel, Florian, and Donald. And then Host came up with a different proof that used the same key idea that transformed the problem into dynamics, but instead of using ultrafilters and some decompositions in L2 of n, the natural numbers, he did everything in dynamical systems. So it's significantly shorter and doesn't use such heavy machinery as ultrafilters and so on. Okay, so the theorem in question is this one here. So theorem one, if we have a subset of integers with positive upper Banach density, so a large subset, then Erdős conjectured that it would contain a subset of two infinite sets. So there would exist subsets B and C with cardinality data of the natural numbers, such that A contains B plus C, like so. And okay, so the plan for today is to get started with some preliminaries, the conventions that we'll take, a few reminders of notions that will be very important for the proof. And then, so I will actually give a proof, a self-contained proof of the length between the combinatorics and the dynamics. And according to how much time I have left, I will also get the proof started. So basically what we'll need is to construct an appropriate topological dynamical system and a bunch of points and measures. We'll see that in a moment. And I plan to get started on that, but we'll see. Okay, so notice that we'll take this sacrilegious convention, or French, I don't know which one is worse, where we include 0 in the natural numbers. And also, as a reminder, now that James is not here, maybe this makes less sense, but okay, so let me just go over it quickly. The upper density is defined as this lim sup of cardinality of A intersection Fn over Fn. And that's the only thing we'll need from combinatorics, really. Next is a bunch of review from topological dynamics. So we will call a topological dynamical system for us will be a pair xt, where x is a compact metric space and t is a continuous and onto map. Now, as it happens, for the majority of things that we'll work on, it's actually a homeomorphism, but we only need onto, as it turns out. And we will use d sub x to denote the distance on x. Okay. Now, something that's very important if you've worked with Fürstenberg systems is the notion of generic and quasi-generic points. So if you give me a point in my set X and a Fjellner sequence, and then a probability measure, we will say that point x0 is generic for mu along Fn if the following equality holds. So this one. If we have that the Wake star limit of the averages of delta masses at the Tnx0 converges to mu. Okay, and here I wrote it out because this is nice and convenient and it's succinct, but what it actually means is this, that for any continuous function, the averages along x0 for the Fjellner sequence Fn converge to the integral. Okay, and something important to notice here is that you may be thinking, okay, so why do I care about this? Usually when I'm doing dynamics, I care about measurable sets instead of just continuous functions. But it so happens that in Fürstenberg systems, the sets that you care about that kind of represent your point, I mean your subset of integers, are actually Klopen sets. And therefore the characteristic function of that set becomes continuous. And this is why we care about generic points and for measures along some Fjellner sequence to establish this length, right? Another thing to notice is that if you have this equality, then the support of mu is contained in the orbital closure, which is going to be the main set we'll work on. This is living inside. Usually it will live inside 0, 1 to the z. Now it's not there yet because it's more abstract. And also it's T invariant, kind of by construction. Nothing too surprising there. Now, another thing we'll need that maybe you haven't seen in a while is the Four Mantlelemma. So what this ensures is that the set of return times, if I return to some open or clopen set, has nice density properties, which are explained here in 1 and 2. And the reason why this is true, let me just write something really quick, is because you can write this as the lim sup as n goes to infinity of the averages, right? So this is d bar fn, so 1 over fn sum n in fn. And now I put in here characteristic of u tn x0, right? So it's the lim sup of some conditional expectations, something like that. And the Four Mantlelemma implies that this is bigger than or equal to the integral of characteristic of u, which is what you would expect. And again, so here, something that we'll see a bit later, the reason why we talk about clopen sets is because these arise naturally in 0, 1 to the z, which is the Fürstenberg system we'll work on. Now, something that...
Yes,
sorry.
I have a question, yes. Who is a Pomentor? I never heard of this name.
Oh, wait, clopen?
No, I mean the Four Mantlelemma.
Oh, maybe it's not a, it shouldn't be capitalized probably. It's just a word.
Oh, this is a word. It's not a mathematician.
Yeah, I don't think it is. I think
okay.
I think it's just a word.
Okay.
Sorry for this confusion. Yeah, but it's just some probability fact. I don't know if anyone can give some better explanation.
It says portmanteau, a word blending the sounds and combining the meanings of two others, which I guess is clopen.
Oh.
It's a dictionary definition. A word blending the sounds and combining the meanings.
Oh no, this is, I see. No, this is not for clopen though. This is just for the lim sup thing. I don't know why it's called portmanteau, but
so I think clopen is an example of a portmanteau, yeah. But I don't know that that's why it's called the portmanteau lemma.
Is this the naming probability, or I just know the fact?
It's just a portmanteau is just a word that means like combining two words.
Yeah, I think it's just a fact in probability.
It's just a probability fact. It's called that. I don't know why.
Yeah, it's just.
Can I? So Andreu, on fact number 2, is this in fact the just density along the Fulner sequence? Like the limit? Does the limit exist there?
Does the limit exist? Let me think.
I mean, I'm just confused because it seems
like I think it does. Yeah, I think you're right.
Open and close. It seems like then the upper and lower should.
Yeah, I think it should be like this.
Okay.
Yeah. Okay.
So, okay, anyway.
Okay. So then, all right. So the other thing we'll need, I'm actually not going to go into the details here, but I can do it later if I have more time, is that because the probability spaces, the space of probability measures on X is compact and metric, because X is compact and metric, for any point in X and for any Fulner sequence, you can go to a subsequence to ensure that X is generic along this subsequence for some probability measure mu. And this is really just a diagonal argument, nothing too big happening there. Now, if you see the word generic without any qualifiers, this is reserved for the Fulner sequence 0 to n, in case you see it in Fürstenberg's book or somewhere else. Okay, so now we're almost ready for the link between theorem 1, which is what we want to prove, and dynamics. And for this, we need Bergelson's intersectivity lemma, which we formulate here. So we have if we have a probability space and a bunch of sets with some bound below for their measure, then we can find some infinite sequence nj such that this inequality here holds, so that any intersection is non-empty. And in fact, because of the sets we're working with have some extra properties, I think we could assume that the NJ has density, but it doesn't matter because recall that all we want to show is that A contains B plus C, right? Infinite. So as it turns out here, just having infinitely many NJ is good enough. Okay. All right. So now the link between combinatorics and dynamics is as follows. So we're going to prove the following theorem. Suppose that we have a topological dynamical system xt, a point x0, and a Klopen subset, so that it allows us to define A as the set of return times for this x0 in E. And as we'll see later, any subset of integers can be realized in this way. Okay, this is the point of fearsome work systems, that any subset of integers is the set of return times to a Klopen set for a given point x0. This point x0 is related to the set of integers. Now, moreover, if we have another point x1, a probability measure on x cross x for which x0, x1 is generic, and furthermore, we have this extra assumption on a good sequence mi, then there exists infinite subsets. So let me summarize this a bit better. So suppose that we have another point x1, and this nu here is going to be adjoining, for which the point x0 comma x1. So the point x1 is one of the points that we'll have to find later in the proof, right? This is one of the important points to construct. And suppose that we have genericity along the some Fjellner sequence Fn, right? And then if we have these two conditions here, we can find infinite subsets B and C. So the point is that these two conditions, namely that x1 can be approximated by mi's that at the same time do this for the joining, is what allows us to find infinite subsets B and C. Okay, so this is one of the main things that I will show today. So let's start with that. Okay, so first of all,
can you scroll back up there? And
yeah.
I just want to ponder that for a moment longer, because I guess that's the crux of this whole thing. And so why is this? I mean, I guess you're going to show us in the proof, but what's the intuition as to how this dynamical thing is related to B plus C?
Okay.
Because
So
this looks like random symbols to me.
yeah, I mean,
Ditto
I
there.
kind of have the same feeling, to be honest. But so the idea is that basically this inequality here, together with the Bergelson intersectivity lemma, is doing the heavy lifting. And then because E is a Klopen set, this allows this condition, this other condition here, to reflect the C. So the idea is that you will be able to construct the B and C inductively because of the Bergelson intersectivity lemma and the fact that these two things hold at the same time. Unfortunately, I don't really have any better intuition for why this is true. So this is maybe too distilled from the original question. So if you want, I remember that what Florian said from a while back, he gave a talk on their own proof. And the idea was something similar. They also used Bergelson intersectivity lemma to show that, so there was a proof before their paper. There was a paper that came out that proved that the conjecture was true if you had the density of the set to be at least 1/2. And the idea is that they were able, so Joel, Florian, and Donald were able to translate or to better express that the condition that allowed them to have this inductive machine that constructed the sets B and C. And this was reflected in the original paper. But as I recall, Florian also said that it was kind of abstract how they came up with the fact that you could keep doing constructing BNs and CNs. So I don't know.
So I don't know if this is related, but is Van der Waerden, Furstenberg's proof of Van der Waerden somewhat related with this, or some idea like that? Because you also have one point going close to the points of interest and so on, right?
Right. That's true. But yeah, I'm not sure, to be honest, because that would be this condition here, but without this, you wouldn't be able to construct the elements in C. So I'm not sure.
Right. Just a question of
Yeah.
if you saw. I mean, also I don't know. I don't even remember the proof, but it sounded familiar from there.
Right.
Yeah.
Yeah.
I don't understand the second condition. The condition that new T. So T,
Sorry. So the set is T minus MIE cross E, right? So these are the two entries. T is only affecting the first one.
I see. So new here is not product measures. Yeah.
It's some joining that still has to be defined. Yeah.
Okay. Yes, that's why.
Mhm.
Okay.
So when you say joining, you mean?
When I say joining, I mean a measure on the product space so a probability measure on the product space such that the marginals are equal. So joining here means nu is a probability measure on X cross X, and nu of A cross X equals mu of A. So it's going to be a joining of the measure mu. It's actually not the measure mu, as we'll see, but that's, and nu of X cross A is measure of A. And here the measure, or if you want, maybe let's call it mu1 and mu2. So joining of mu1 and mu2. And those measures have to be defined yet. Yeah. So the thing is, this is still very abstract because we still have to construct a system so that all those things make sense for our starting set A, right? So we'll see that later. I don't think we'll get through this part today, but.
So just to be sure, every product measure is a joining, but not every joining is a product measure.
Correct. Yes, that's what you should have in mind. And also, you should also have in mind the diagonal joining. So for example, if you're joining a measure with itself, you can define the diagonal joining by something like this. This is something very useful to keep in mind. But anyway. All right, so now let me show you the proof, and hopefully the proof will elucidate things a little more. All right, so let's get started. So we have a bunch of conditions, but the ones that I want to focus on more are these two here, the convergence to X1 and the bounded from below measures for these particular sets. So, okay, so since we have this, and I just talked about Berthelsen's intersectivity lemma, that's what we're going to do right away. So we start by applying lemma 1, which is intersectivity lemma. So that, okay, so if you want, I can go to a subsequence, but just for the sake of not overloading notation too much, I'm going to say that so that without loss of generality, so I still have this along mi, and for all r bigger than or equal to 1, nu of the intersections is positive. Okay, and I'm going to give this a name. So I have to give this name 3 because I will be using it later. Okay. All right. So this is the first step. Then I'm going to define the set of return times to X1. I'm going to give it a name L. So it's going to be the L's in N, so that TL X1 belongs to E. Okay. Now, the next step is the following. So observe that the point x0, x1 returning to a set of the form t to the minus mi e cross e means the following. So this is, what am I going to say? If and only if. So what does it mean? So the first one, Tn x0, must be in t minus mi e. And the second one, Tn x1, must be a member of E. So in other words, this means Tn plus mi x0 is in E. So nothing weird going on so far. And Tn x1 is in E. Now we'll recall the definitions. For the first one, that means that n plus mi is in A. Is in A. And n is in L. That's the second one, right? Recall that A was defined here. It's a set of return times to from x0 to E, and the second one is from x1 to E. But now I don't want to write it like this. I want to care only about the n. So I want to say n is in A minus mi, and n is in L, which of course can be translated as n is in the intersection, right? Okay, that's the first step. The second step is to realize that this inequality 3, together with the Four Mantlelemma, implies the following. So use Four Mantlelemma, which is 2. This is 4. And 3 to deduce the following. So we're going to have the density of along Fn of the intersection A minus mi intersection L is positive. And this is true for all R, again, because of 3. I cannot say n because there's some nonsense. Okay. So like this. So the reason why, again, you can reinterpret this as a lim sup of characteristic function, the characteristic functions of these guys. And because of that, and the Four Mantlelemma, and because E is a Kolpin set, you get exactly what you need. So maybe let me just interpret this density as a limit for the characteristic function of, well, the intersection of t minus mi. Like this. And then you'll get exactly this intersection. And now the fact that this holds is exactly what's going to allow us to construct the sets B and C. So now we construct B and C inductively as follows. Okay. So I'm going to call B Bn, sequence of increasing numbers, and C is going to be Cn. So I need to construct B1, B2, etc. And I'm going to ask that they have the following properties. So, okay, so maybe we'll focus on the sequences. So construct Bn and Cn with the properties as follows. So Bn, first of all, will be in the MIs that I know work well. Then Cn is in L, and also Bi plus Cj is in A for all I and j. For all I, j greater than or equal to 1. So this condition here is exactly what's saying that B plus C is inside of A. And recall that A was any set, so that finishes the proof. But the point is that if I also ask for this and this condition, I can make all of this hold at once and proceed by induction. So, okay, so I think the first one is, okay, so we're going to start. Oh, sorry, damn it. I want 0 here for some reason. So choose the first one. C1 is an L arbitrary. No, I had it right. Damn it. Sorry. Arbitrary. And suppose that the other ones have been constructed. And they satisfy this. Right. So what I need to do is I'm going to start by constructing a C sub n plus 1 that satisfies that it's an element of L, but also for which bi plus Cn plus 1 is an A for all I between 1 and n, right? So for this, I'm just going to use this fact, right? So because B1 through Bn are in Mi by assumption, then this was called, it doesn't have a name. Maybe let's call it 4. By 4. Goodness. Okay, I'm being a bit wasteful with space, it seems. So by 4,
just in case you didn't know, you can add a page in between.
yeah, how do you do that?
So if you go to the upper right under the battery symbol, there is those like 2 pages. Tap on that. And now go to the page that you're currently writing on. Yeah. And go to the lower left corner of that page and click on the options, and there's an add page.
Okay, great. Thank you. Yeah, yep. That helps. Okay. I was going to just go to the end, but that's much better. Okay. So by 4, this intersection is non-empty from 1 to n of, what is it, A minus Bi, right? Because the Bi's are in the set of the Mi's. Intersection L, this is non-empty. In particular, it has positive density. So I can choose the Cn plus 1 from this set, but also I can choose it so that it's bigger than C1 through Cn. So this way I make sure that my sequence keeps increasing. So pick Cn plus 1 from this set. And Cn plus 1 without loss of, sorry, this is a bit too large. It's bigger than Cn without loss of generality because it's a set of positive density. Now, by construction, Cn is in L, clearly. Cn plus 1, I mean. And also, Cn plus Bi is in A for all I less than or equal to n. So we're in good shape because this Cn plus 1 satisfies all the conditions that we want in star to keep the induction going. So really the only next step is to be able to construct the Bm plus 1 that works. So, okay, so let's see. Here. All right, now, since the set E is an open set in particular, since it's a Clopin set, we can choose some Mi such that the following holds. right? And this is by the convergence property, and because the CJs have all been established and have been chosen for now from 1 to n+1. So since the TMI x0 goes to x1, I can, and E is a Clopin set, I can pick some MI that is convenient enough that works for all the J's at the same time. And now this is exactly what I need. So moreover, I can also ask, since it's an infinite set, right? I can ask, may M sub I should be bigger than B sub n, the previously largest one, right? Because we have infinitely many of them. And now by construction, I also made sure that Bm plus 1, okay, so choose, so, sorry, I want to actually initialize it. So let Bm plus 1 be this Mi. And so by construction, what I have is that Bm plus 1 plus Cj belongs to A for all j less than or equal to n. And because of that, that means that we're actually done, because this construction can be kept going indefinitely. Okay, so I don't know, Sohail, if that helps you understand why the conditions were taken like so. So the idea is, the key point, I think, is being able to use this set for any R, right? So using Bergelson's intersectivity lemma with A minus Mi and L is what allows the construction of the infinite sequence, really. That's the, I think that's the essential part. But you can still ask, but how did you come up with this condition? And I think that this condition also appears in Joel's and Florian's and Donald's paper. And they said that, I think Florian said that this condition was taken from the original paper that did it for density bigger than 1/2. And it's kind of this, I mean, just getting that thing to work for 1/2 was a breakthrough, right? So it's,
I mean, condition 4 actually seems natural to me, or it just looks like it makes some sense. Because
I see. So the point is that, okay, so let me put it this way then. The point is that this condition allows for condition 4 to hold because you chose the sets E and x0, x1, etc. conveniently to understand the situation. But so I guess the point is, how do we translate condition 4 from combinatorics to dynamics? And the point is to use this weird joining trick together with the convergence that we can think of as the van der Waerden, as Rigo said, right? Idea. But I mean, to be honest with you, this to me is just, okay, it just works, right? But I'm not sure how they came up with it.
The A minus MIs is obviously the
Right.
We want all of those to have a decent sized intersection, because that's kind of like getting B minus little c and then
yeah
intersecting them. And then I just assume that the L, it's kind of like
the L is the connection with the other infinite sequence, right?
Yeah. I like to think about L as like not literally a central set, but something like a central set, some very rich set that's going to give you properties in addition to just being infinite or upper density, which is what we have without L. So like we want something with upper density, but we also want some other combinatorial or L number theoretic property. And presumably L has this extra property. So we don't want just our intersections of the shifts to be empty. We want them to intersect this combinatorially rich set to continue to allow us to do shifts as well.
Right. And L is actually a set of return times as well. It's just for the point x1. But yes. Okay. So then with that, now we can continue and start constructing. So now what we need to do really is we need to construct the appropriate x and little x0, that's not the hard part. The hard part is to get the x1 and the joining, right? So I would say this is the hard part. And also because they have to satisfy these two conditions, right? But today I'm just going to stick with the easy part. So, okay. So starting with the construction of a system. So what we're going to do is a series of steps. And we're going to start with a system that's not going to be the final system that produces what we need for theorem 2, but we can keep modifying it, and that's what we'll do in order to get the desirable system. But okay, so we start with a set of integers with positive density. Let's say that the upper Banach density is some delta bigger than 0. And what we do first is the traditional construction of the Fürstenberg system without really any weird modifications yet. So what we do traditionally is we let x0 be the sequence given by our set A. So this uniquely identifies A inside of 0, 1 to the z. And we endow 0, 1 to the z with the traditional shift. I just wrote it here. I think everyone here has seen it before, so I don't need to go into more details. And then we start constructing the system. So first, since what we're going to care about is some Fjoner sequence, and we're going to construct the measure in the usual averaging scheme, we will only really care about this, namely the orbital closure of the point x0. So all the dynamics are really happening for this subset of 0, 1 to the z. We don't really care about the whole thing. Then the Klopen set of interest is the set of x's that have 1 at the first coordinate. If you've seen Fürstenberg correspondence before, which I think you have, you know that this exactly corresponds to, so you will see that, maybe let me do it in red. Sorry, I have it here. So, so then the set A can be realized as a set of return times to this Klopen set. And this is really just, if you unwrap the definition, that's what it is. Then what we care about next is the construction of an invariant measure that is suitable for our purposes. So it has to see the set E correctly. And for that, we just pick a Fjoner sequence that realizes the upper density. Let's say it's Fn. And now, without loss of generality, we can assume that x0 is generic along some Fjoner sequence for some measure mu. In fact, what's going to happen really is that this is, so mu is actually, it's equal to this. Yeah. So it's written a bit abstractly, but really the measure mu that does the genericity and property 4, which is what we care about, is just obtained via the averaging scheme like this, which I'm sure you've seen before with a Fürstenberg correspondence. And now you can check that this measure mu satisfies that it gives measure at least delta to the Klopen set E. And this is again by portmanteau. We agreed that we would do it with lowercase. Okay. Okay. So this is the first system. What we're going to do next is we're not going to be happy with just any system, because it's possible that mu is not ergodic. So we're just going to use the ergodic decomposition and get an ergodic mu, but we're still going to satisfy these properties 1, 2, 3, and 4, right? So what we do is, okay, so we use the ergodic decomposition. We write the measure mu that we had above, we write it as an integral of ergodic measures. So mu omega is ergodic for lambda almost every W. Okay. Now, we want the ergodic measure to satisfy the same properties 1 through 4. So at the very least, we need this. So, but that's fine because by definition, the measure of E is equal to the integral of the measures omega evaluated at E. So at least many of them have to give it measure at least delta, right? If all of them had measure below delta, it would be impossible just by a pigeonhole principle. So we can just pick one mu sub omega. Let's call it mu prime. And now, of course, this mu prime will have mu prime of E bigger than or equal to delta. But recall that we want, so this is still a measure on X, so that's fine. E is still a clopin set, but we want X0 to be generic, right? Along some Fulner sequence. But as it turns out, this is something very important that I think, since I have some extra time, I can talk about it in a bit more length. The point here is that whenever you have an ergodic measure on an orbital closure like this, then you can always realize this measure as a weak star limit for some averages, for some Fulner sequence. This Fulner sequence may not be the original that you started with. So if here was Fn, this Fn here could potentially be different. But what we're going to do is, okay, so here I just said, right, I conveniently said it's generic along some Fn. So now if I change mu for mu prime, I just have a different Fn, but let's keep calling it Fn for the sake of simplicity. And for this Fn, I still have I still have an equality like this one, which is what we care about. Now, okay, and that's really all we need for this part, so that we can assume part 5 that mu is ergodic under T. Right now, so let me also briefly summarize what comes next. This I haven't prepared. So the next steps are as follows. We're going to have to change the system and the mu again. But now what we're going to do is, so for any given system, you have the Kronecker factor, right? But it's not always the case that the factor map from your starting system, even if it's a system with a topology, it's not necessarily the case that the Kronecker factor map is continuous. But there's a trick, there's a way, we'll see, that we can change the Fulner sequence again and make sure that the Kronecker factor map is continuous. Then based on that, we will also be able to pick the X1 and construct the joining. Once we have all these things, all that remains is to construct the sequence of MIs that we used in theorem 2. And then, so the last thing, I don't know if I'll have time for this in the next time I speak. There's a proposition in Host that kind of addresses a question that appears in the paper by Joel and Florian and Donald, which is, well, so we did B plus C. Is it possible? So this is still an open question. Given A and Z with positive density, do there exist B and C and D? Let's just say infinite. Such that A contains B plus C plus D. So, okay, based on their theorem, it's natural to try to see if, well, can I assume that A contains, let's say, B1 plus B2, and B1 has positive density? Because then I could apply the theorem again and be done, right? But proposition 2 in Host shows that this approach fails. There are sets for which you cannot have infinite set plus set of positive density. So proposition 2 shows this approach fails. And it's just a concrete construction. So I guess it's, if I don't have time for it, it's not too bad. You can read it on the original paper. Shows that this approach doesn't work. Okay, so let me just say a few words about genericity. So I just want to say a few words about this result that I think is very important. So if you have a compact metric space and we have a point such that it realizes X as an orbital closure. Sorry, I didn't initialize this. Let's say that it's, let T be a homeomorphism. Let's say that such that we have X is Tn X0 closure. And now suppose that we have an ergodic measure here. Then it must be, so then there exists some Fjellner sequence such that the measure mu can be achieved as a weak star limit like so. Okay. And the key idea here is, so I'm just sketch the proof briefly. So the first step is, okay, we have an ergodic measure, ergodic probability measure. It must have at least one generic point, right? So by Birkhoff's ergodic theorem, there exists at least X1 such that this is true, right? This X1 must be an X, of course, equals integral f d mu. And this equality is for generic functions, so that means that that holds for every f continuous. Okay. Now,
Andreu, can
yeah.
you scroll up to the statement of the lemma real quick?
Yeah.
Or go to probability measure on X. And so X in this case is just any compact metric space. No.
But it's any compact metric space that can be realized as an orbital closure.
Ah.
So as long as you have a point with dense orbit, then all the measures, all the ergodic measures can be realized in this way.
Okay.
Yeah. So if you want, so you should read it like this. So this is just an aside. So read the result as and the point here is that, so the reason why we care about this is that this X0 is actually the one that, so when we're doing Fürstenberg systems, the X0 is the one that understands the combinatorics of this of the starting set. Okay. That's why we don't really want this X1 here, because this is something that would always be true, right? We always have a point for which we have genericity by the Pointwise-Ergodic theorem. But what matters really is that we can relate it to the starting X0 point. So this is maybe a bit subtle, but it's really essential to be able to apply all those Four Mantlelemmas and so on, right? right? So to be able to bridge the dynamics with the combinatorics, caring about this versus the x1 is essential. And so, okay. So I'm just sketching the proof here. So you start with a generic point, which you don't like, but then you want to change it for the x1. So for the x0, I mean, and the price that you pay for doing that is that you no longer necessarily will be using this averaging scheme. You will maybe change it for a different Fjellner sequence. So what happens is, okay, but since x1 is in the orbital closure, so you inductively do the following. So you do a diagonal procedure. Okay. Some m sub n, capital N, such that, let's say, the distance from mn plus n x0 and x1 is less than 1 over n. And what you achieve with this, and okay, sorry, I missed something crucial, right? So every time you keep adding more and more n's, and you're now comparing the x0 along some subsequence. So what happens is now, if you go from, so now you can change this average for the average along mn plus n. So now you'll have limit n goes to infinity, because you have uniform continuity. Use uniform continuity to deduce. And you have to use a diagonal argument, right? Because you have to make sure that this holds for all f, but you can keep adding. So you can use a dense subset of C of x and so on, right? You see, okay, maybe I should. But now all this is doing is it's changing the Fjellner sequence. So this gives, so I have to use to account for all the f's, right? But C of x is separable because x is separable. Well, it's compact metric. And then the mn's potentially change. The Fjellner sequence that you started with for some new one, right? Like it starts at mn.
I have a question that the m n here is depend on small n or big n?
Depend on capital N.
Capital N. How
Yeah.
can you do that to make sure?
Right, because so, I mean, you have only, so you fix in a capital N, right? And you have, so you have the TMN can approximate X1. So, okay, maybe. So if this is very small, yeah, like this, then no matter how many times you apply T, if it's a finite number of times, right? You can say, because it's like this.
Okay. Yeah, I see.
For only these many n's, right? Yeah, that's just what that's why you have to be careful with the diagonalization. That's what I meant. Okay, so I don't have anything else. That's all for me. The next time we'll try to address these points here. All right. Are there any questions?
This like genericity's lemmas only work with when mu is ergodic. It's not true for any invariant T invariant measures.
Yeah, you need ergodicity. Yeah, but yeah, I guess the point of the lemma is that so here, where was it? Right. So here, so what you care about is that you can still relate the measure that is ergodic to the point x0 that is telling you about A, right? So you want ergodicity, but you want to still remember the combinatorics. That's really what it is. But as it turns out, because so this is also part of the reason why we use this guy, the x as the orbital closure, because it allows us for the ergodicity of mu to not be an obstacle to still have good combinatorial consequences because of this result of Fürstenberg. This is somewhere in the book that he published. This result I talked about last here. This one. If you want, I can give you a better reference. Like I can give you the page and everything.
So host didn't like reprove this one. He just like quote Fürstenberg's on the.
Sorry, say that again.
Lemma. So host didn't like reprove the last lemma. He just quote Fürstenberg's book.
Oh, so I think in this paper he reproved it for the sake of completeness, but it's an old result. Yes.
Okay.
So I think that if you go to the paper, you will see more or less this argument that I wrote over here. So he maybe even gives more details than I did.
Interesting.
It looks like there's no more questions, so maybe we can give our speaker a round of applause, end the recording, and then if anyone wants to stick around, they can stick around. So thank you for the talk, Andreu. I certainly learned more than the first time I attempted to read through that paper. So thank you for suffering in my place.
Sure.
Yeah, at least I learned the word portmanteau today.